Hello, my name is Yahya AYDEMİR. I'm a second year EE student at Bilkent University, and today I will be presenting you my Physics 212 project. Me and my group members try to make a quantum characterization station which aims to measure or calculate some of the properties, quantum properties of the matter. The first thing we try to measure or calculate is the bandgap energy of a PN junction, a diode. To do it, we take some voltage measurements at different temperatures for a diode, and then graphing it, we try to make a guess about its bandgap energy at 0 Kelvin. The second thing we try to measure is the Boltzmann constant. To do it, we first make a steady current flow through a diode, and after doing that, we measure its voltage at different temperatures, and using these values, we try to make a guess about the Boltzmann constant. The third thing we try to measure is the Planck constant. To do it, we used different light emitting diodes with different wavelengths, of course. And after measuring their threshold voltages, we calculated the Planck's constant. Fourth thing we try to measure is the temperature coefficient of the metals. To do it, we first measure the metals' voltage levels at different temperatures, and after dividing it to a stable current, we calculate their resistances, and using them in the formula, we try to measure the alpha coefficient. And finally, we try to measure the Seebeck coefficient between copper and iron. To do it, we first connected two cables, two wires, which one of them is iron and one of them is copper. And after doing that, we heated some side and we then cool the other side, and then we try to find the voltage across the junction. And after doing that, we try to measure or calculate the Seebeck coefficient of these two metals. Now I will be presenting you the findings of our experiments. At the heart of our measurements, the Peltier cooler is the fundamental thermoelectric device we used to set the desired temperatures within the thermal chamber and to create controlled temperature gradients, as in the Seebeck experiment. The AD620 allows us to boost extremely weak thermoelectric signals, especially at the microvolt level, to readable levels by minimizing common mode electrical noise. The constant current circuit we build minimizes data collection errors by providing a completely stable current to the samples, unaffected by temperature changes. The thermal chamber, where we place our samples, is constructed from aluminum plates and insulation materials, rock wool, allowing us to conduct our experiments in a stable atmosphere isolated from the external environment. Finally, the PID temperature circuit with max 31,865 and PT100 measures the chamber's instantaneous temperature with high precision sensors and continuously adjusts the heating and cooling power using a PIT control algorithm written in Arduino to keep the environment stable at our target temperature. While finding the bandgap energy, we examined the relationship between a diode's voltage and temperature, and then calculated the bandgap energy as 1.24 electron volt from experimental data, compared to the theoretical value of 1.14 electron volts. Although our linear graph aligns with the theoretical model, we observed some margin of error in our measurements. The main reasons for the deviation might be a non-ideal diode behavior, series resistance effect, and minor temperature variations at PN junction. Nevertheless, our findings clearly demonstrate that as temperature increases, the diode voltage decreases linearly as predicted. In our Boltzmann constant measurement, we analyzed the current voltage characteristics at different temperatures and reached an average value of 1.34 multiplied by 10 to the minus 23 joule per Kelvin. When compared to the theoretical value of 1.38 multiplied by 10 to the minus 23 joule over Kelvin, we achieved a highly successful and close result. We attribute slight deviations in the data to instantaneous temperature fluctuations during measurements or low-level electrical noise in our precision circuits. Ultimately, the distribution of our data points successfully reflects the fundamental physical relationship between thermal energy and temperature. Using the threshold voltages and light frequencies of different colored LEDs, we calculated the Planck constant to be approximately 8.46 multiplied by 10 to the minus 34 joule second. Given that the theoretical value is 6.63 multiplied by 10 to the minus 34 joule second, we encountered a more noticeable margin of error here compared to the other experiments. The primary causes for this error are the non-ideal structure of the LEDs, internal voltage losses, approximation of wavelength values, and general measurement uncertainties. Despite this, the linear relationship we observed between voltage and frequency experimentally verifies the fundamental principles of quantum mechanics. While measuring the temperature coefficient of resistance, we used a copper sample, and then we found the material's temperature coefficient of resistance, or its alpha value, to be 0.00412 over Kelvin. This partially successful result, which is quite close to the theoretical value of 0.00393 over Kelvin, clearly demonstrates the expected linear increase in metal resistance as temperature rises. The slight margin of error we observed is likely due to the contact resistance, impurities in the wires used, or an uneven temperature distribution across the sample. We measured the thermoelectric voltage using a temperature gradient established on an iron-copper thermocouple and calculated the Seebeck coefficient as 14.21 microvolt per Kelvin. We obtained a highly consistent result with the theoretical value of 13.17 microvolt per Kelvin and verified that the voltage increases proportionally with the temperature difference in the system. The minor deviations encountered in the system might stem from imperfect thermal isolation or weak external noise interfering the signal.